Okay, let us start with two announcements. So first, it might happen that today we'll talk a bit later. I mean, more than 2 hours, and then you will have a shorter exercise session. This is because I need to finish some chunk of material. Because next week I'm not here, and so what's going to be next week is an extended exercise session, which is important. I mean, so you are going to prove some important facts, you know, like exercises, just to do some important computations. Okay, and then where are we? Well, I need your help. I found some chalk for first half an hour. Well, so we are going to prove Donsker's theorem. What's that? It justifies the very original view on the Brownian motion as the limit of random walks. So we deal with a sequence of ID random variables. And then we consider their sums. Interpolate in between of integer times linearly. Like that, and rescale the corresponding piecewise linear process by square root of n in space and by 1 over n in time. Let me put here tilde just to make the notation a bit more, you know, a bit more distinguishable. So what's that? This is just 1 square root over n s and t. I hope. And the theorem says that this guy's converges in distribution to bt t, say 0, 1. And in distribution, again, it means that there's random variables in the space of all continuous functions. Namely, this is equivalent to say that any functional converges to the same functional computed on BT. And when I said it last time, it was another, you know, unconscious reflex like in the very first lecture. So I just said that bounded continuous functionals are measures, which is a complete absurd because linear bounded functionals are measures. And what we need here is bounded functions on the whole space, I mean, which is unbounded itself. Okay, so those are not measures. It was a complete absurd. Sorry for that. Okay, so how the proof goes? It's quite standard two-step procedure. So step 1, we will go to prove tightness of this distribution. So tightness of these guys till there. So those can be thought about as measures on C01, right, on the space of all continuous functions. And okay, this is something that guarantees that we can find the convergent subsequence. Means convergent subsequences. And step 2. Well, here some work should be done, and step 2 is just to characterize of the characterize the limit? Well, if we are able to prove that any possible subsequential limit is something very concrete, then it means that the whole sequence has a limit which is characterized by this. Okay, this is a very standard two-step proof. So, okay, what is step 1? Basically, we should not expect any difficulty here, right? Because it should be something like central limit theorem. So those are random walks, and if we think about distributions at a given time, those are just sums of independent variables, so it must be easy. Okay, for step 1, what do we actually need to check? So there is an abstract statement. If the space C01, where is it here? If it was a compact, a metric compact, then there is no problem, right? Because on the compact metric space, the space of all probability measures is already weakly compact. The problem is that it is not a compact, so there are unbounded functions. So Prokhorov theorem, I hope most of you know what it is. Basically, it says that we should check the following. So this is a very abstract statement. So we should check that for any small nu, the probability that there exists a compact, this C01, such that the probability of the event that our S tilde is in this compact as a function of t. Let me erase t here. I mean that this function is in a compact set is greater than 1 minus nu. As eventually as n tends to infinity. So basically, well, okay, if you never saw it, what is the problem? Say, just imagine the random variables with real values. Okay, so you have a random variable with a real value. If a sequence of them, if they're all uniformly bounded, then you already know that there is a subsequence conversion in distribution, right? This is some abstract fact from functional analysis. The problem could be is that if they support moves to infinity, say X0 is concentrated around the origin, X1 around 1, X2 around 2, etc. Right? Then when you try to think about the limit in distribution, what you see is just the zero measure. Everything escaped to there. And this criterion is exactly what prevents it. And the message is that it holds in a fairly general setup. That there is no need for this space to be a real line. I mean, it's just submetric space. Okay, so here is what we should to check. And then there is another fact from functional analysis, Arcellas-Colli theorem, which basically describes the compact subsets of the space of continuous functions. So the space is compact or pre-compact if the functions here are uniformly bounded and equicontinuous. Check uniform boundedness of these guys and equicontinuity. With probability at least 1 minus, okay, for any nu. So given nu, we should find such a bound and such a modulus of continuity that this function, is nice with probability at least 1 minus nu. Okay, good. So to do so, I need a lemma, which is very simple, and on the contrary, it's just some completely trivial computation, though rather elegant. It's usually attributed to Ottaviani, but unfortunately, I don't know the exact reference. So, okay, what's that? Imagine that we have a sequence of independent variables, not necessarily identically distributed. So what I have in mind is identically distributed, but just independent. n-centered and has finite second moment. Somehow the proof could be done easily if I assume that there is 2 plus epsilon moment, but I'm just going, you know, to do it in a fair generality. So imagine that we have a sequence of such variables. Then for any alpha and any n, the probability that the maximum over 1n of their partial sums, okay, let me be m, like there, Sm is again the partial sum, is greater than, say, 2 alpha, is bounded by the following. There is something here which is just the expectation of Sn squared over alpha squared minus 1 by the probability that Sn itself is greater than alpha. Okay, so what is the message? The message is that we can control the distribution of the maximum using just the information about the very last sum. Okay.
Are they identically distributed or?
Nope, not necessarily. Okay, I'm going to apply it to identically distributed, but in the lemma I do not need. So, and what is the proof? The proof should be fairly easy. So just denote this event by omega, this maximum. And actually, this is very much related to the course on martingales you have on Mondays. So just denote this event by omega and decompose it into disjoint sets where each of them, say, okay, here omega k is the event that sk is greater than 2 alpha, but all the previous ones are strictly less than 2 alpha. Okay, so basically k is just the first time I see this huge value. Okay? So now what is the idea? The idea is that if now I'm going to go backwards. So I'm going to estimate this from below. So what is the probability of this event? The intuition is that if we have a big sum somewhere in between, like here, we crossed to alpha, then of course we have a big chances to stay there, right? And not to go backwards to the level alpha. Okay? So I'm just going to estimate this from below by the event that happened. Okay? This is greater than sum over k probabilities of omega k. And, okay, let me intersect it with the event that Sm minus Sk is less than alpha. Okay. Is clear what happened until now? I mean, I just say, okay, I would like to estimate the probability that I'm outside of the range alpha here at the moment m. What I do, if I already crossed the level to alpha, then, okay, if the rest is less than alpha, then I definitely stay above. Okay?
You have to sum out from 1 to n.
From 1 to n. Yeah, thanks. And here it should be n as well. Yeah. Thanks. Okay. Now what I use is independence. This and that are independent. because this depends only on the first k variables, and the latter depends on the rest. Okay, so this is basically, Don't worry, it's going to be short. I mean, so I need just one line. So this is just the product of probabilities. And this probability can be estimated from below, like 1 minus the probability of the bad event, that this is big, estimated from above, which gives this bound. So what I claim is that we are done, because I can continue and say this is greater than this expectation. Okay, and then what I have is exactly what I need. P of omega. Any questions? Yeah, well.
Why those ends are independent?
Just because omega k is contained in the sigma algebra generated by the first k variables, right? Including the case 1. But this increment is generated by everybody excluding xi k. Okay, so that's just the rest. Second.
And the last inequality?
Here? Well, just decompose Sn as a sum of the increments of Sk and Sn minus Sk. They're independent and centered.
Okay.
So, okay, that's fairly elementary, but you know, still it's very useful. So, good. Now, let us proceed with Donsker's theorem. Okay, here is the bound. Okay, now uniform boundedness of S tilde. What we need to prove is that for any nu, there exists such a constant m, such that the probability of the maximum over 0, 1 of Sn T is smaller than n with probability at least 1 minus 1. So this is the first condition here in the Arcelor-Ascoli theorem. Okay, it must be exactly the setup here, right? Because remember, this is a piecewise linear interpolation of progressive sums. So basically, this is nothing but the probability that the maximum over k from 1 to n as k is less than m square root of n, right? Because we had this rescaling. And then, well, what I need to prove is that the probability is greater than m square root of n is bounded from above by something small. Okay, well, this is straightforward. So this, by the lemma, is bounded from above by what? By 1 minus what is the variance of Sn. This is n, right, with some n independent variables. So this is n over m square root of n squared minus 1. So here there is no problem. This is morally 1 if m is big. And then this is the probability that Sn is greater than whatever m square root of n over 2, right? And this is under control because we have the central limit theorem. So by the central limit theorem, this converges to, well, to something, I mean, to constant over m square root of n exponential minus m square root. And, oops, no, wait a minute. So I haven't rescaled here, right? So it should be that the standard normal variable is greater than m over 2. So this is like that. Okay? So now what I'm saying is that if m is large enough, then this is less than nu. If m is chosen large enough. It's clear what happened. So just, I mean, somehow more transparent way of proving this is to use some martingale inequalities. But typically then you need some higher moment. And so what I'm doing is just avoiding just using these probabilities to converge. Okay? So this is uniform boundedness. And the second thing we need to check is, well, equicontinuity. What does it mean? It means again that for any epsilon and for any nu and for any epsilon, we should be able to find delta such that the probability of the event maximum overall t minus s less than delta Sn t minus Sn s is greater than epsilon with probability less than nu.
This is for all epsilon.
Oops, yeah, this is for all epsilon. Thanks. Okay, so this is what we need. And let me put whatever, maybe 6 here. Maybe 2 here, it's not important. Just for convenience. Okay, so what is the idea? How to do so? And let me erase the concluding line of the proof of dilemma. So, thanks. So, okay, we have the segment 0, 1. What I'm going is again to use that lemma about progressive sums. Let us split this segment into roughly 1 over delta subsegments of size delta. Then what I'm saying is that if for 2 close points this difference is huge, it means that one of the differences between, say, here and here, or maybe here and here, or maybe here and there, is also huge. I mean, the idea is that it's enough to control the increments with respect to 1 over delta points here. So if I know that all these increments over the segment are under control, then I'm done. So again, more rigorously, what I'm saying is that, okay, first let us rewrite this condition in terms of unrescaled sums. Square root of n sk minus sl is greater than and it should be here m, of course, less than nu. Basically nothing happened, I just rescaled everything back. And then what I say is that it follows if I can prove that the probability of the maximum over k, okay, let it be another letter like s less than delta m of s m plus k minus sm is greater than, say, 2 epsilon square root over m is less than mu over 3. Sorry for that, by another delta. For each of m equals, say, 1, n 1 over delta, 2n, 1 over delta, etc. What it should be? It should be n over delta so I have 1 over delta segments, right? And I'm, no, that's not it doesn't work. I mean, it's n delta, 2n delta, etc. Like this. Do you see what I mean? I mean, these are just points. I mean, mark it here. I mean, these ones.
S or K?
It should be, oh gosh, yeah, it should be S. Yeah. And I'm totally missing the indices here, so sorry for this. Why 2 here? Just because I say, and I do not need to divide here, but it's of no importance. I'm just saying that, okay, if all these three, say, okay, if I have 2 points on different intervals, say here and here, then I say that let me control these 3 increments. If they all are smaller than 2 epsilon square root of n, then I'm done. Okay? Good. And basically I have just 1 over delta 1 over delta intervals, so when I multiply here, I have my nu back. Maybe to be really, you know, really rigorous, you should also divide by 2 here or something like that to be on the safe side. Okay, good. But now I can apply again, my lemma, and to say that I have some control of this probability, right? So this is less. Is less than what? Then again, 1 minus the variance. What is the variance? The variance is, let me put here some universal constant. The variance is roughly delta n. Okay, it might be non-integer, then you put the integer part, but okay, roughly, this over 2 epsilon square root n squared. Okay? And then this is again the probability that the sum of delta n random variables is greater than something, and this probability is exactly similar. I mean, this is exactly the same computation. Is what? So it's again some constant over. So this is the probability that the random variable with the variance delta is greater than epsilon. So this is square root of delta over epsilon, right? Exponential minus epsilon squared over 2 delta. Are you okay with what I wrote here? So this is the probability that the normal variable, standard normal variable, is greater than epsilon over square root of delta. And this is exactly what we need here. Okay? And again, what I claim is that it can be made strictly less than what we need, provided delta is small enough. Any questions? Well, there is some technical issue a bit hidden. So now what I need, in fact, to use is that, here it was also a convergence involved, right? I used the central limit theorem. So I used this convergence to the standard normal variable. And here what I'm actually doing is using the central limit theorem 1 over delta times, right? Because I need it for each of the segments. But actually there is no issue, because first I fix delta sufficiently small so that I win eventually, right? And that is just a fixed number. So I can use just a constant number of times the central limit theorem. Okay, so this is the end of step 1. So step 1 is done. And as I promised, step 2 is fairly easy. So there is almost nothing to discuss. So step 2, let us just think about finite dimensional marginals. So for any given times, let us think what is the limit of what is the joint distribution of these values. Roughly, this is just distribution of 1 over square root of n s in t, 1 over square root of n s in t2, etc. Plus some errors, right? Plus, the difference between it's just I wrote a sum of 2 vectors. And then the first term does converge to the normal distribution by the central limit theorem, because the increments here are independent. Okay? So the first converges to BT1, BT2, etc. just by the CLT. Right, because I apply it to this, to the difference st2 minus st1, to the increment st3 minus st2, etc. Everything is independent. And this converges to 0 just by well, by trivial estimates, because this is the probability that of a single that a single variable is greater than square root of n. I mean, the probability that this is big is the probability that a single variable with this index is greater than square root of n. Okay. And we're done. So, here, this comment is again CLT for S into 1, S into 2 minus S into 1. And we know that the distribution, that we have a random variable in this space, which means that the trajectories are continuous, just by the very definition of the space, right? And so it's enough, if we know all the finite dimensional distributions, it's enough to know the whole distribution. Okay? So good. It's a good moment to ask something about Donsker's theorem, if you wish. Well, if not, then let us summarize what we have right now. So what we have right now are several constructions of the Brownian motion, like in one basis, in another basis, starting from finite dimensional marginals, and the theorem, the Donsker's theorem, which says that this is indeed the limit of all reasonable random walks. Okay. The next part of material is again something about the properties of the Brownian motion. Well, but that's going to be slightly more involved than it was, partly due just to the terminology. So what we are going to discuss next is Markov property of the Brownian motion. Well, also some computations, and also some martingales. Again, let me start introducing the terminology before the break. Maybe here. Okay, so terminology. And this is going to be very much related to the Markov chains and to martingales in discrete time, etc. So first, okay. I need filtrations in my probability space. So I have a huge probability space, and by filtration, it can be again 0t or 0 infinity or 0t not including t, or some discrete subset or whatever subset of indices. It doesn't matter, but let me write this way. Well, this is just a filtration, which means an increasing family of sigma algebras. Let me denote them other way around. And everything is in my huge sigma algebra of events. Okay? So then, also, as usual, it might be useful to assume that already phi naught contains all the events of outer probability 0. All the events that are contained in some measurable event of probability 0. So it might be useful to assume that this is complete. So, okay. Let us always assume contains all R such that with probability 0. Okay, good. Then there is something which is specific for continuum setup and which doesn't disturb us in discrete. Let me introduce the notation ft plus. So what's that? By definition, this is just an intersection of everything which is after the time t. Okay. Well, trivially, this is still a sigma algebra, so of course it contains ft, but in general it does not coincide with ft. Okay, good. Then we say that xt is an adapted process with respect to this sigma to this filtration, this family of sigma algebras. What if its trajectory until any given time, say, is measurable with respect to this time? Okay, just some formal definition. And somehow the very useful way to think about this definition is just to define. If we already have some process, say we already saw the Brownian motion, so just define ft to be sigma algebra generated by all those variables. Again, real mess with indices. So fs be sigma algebra generated by all those random variables, meaning that the measurable sets, I mean, this is the product sigma algebra. I mean, you just take any fixed collection of times, and the basic measurable sets are like xt1 is in B1, and xtp is in BP. Consider events of such sort.
We want also to add all events of probability 0.
Yeah. I mean, so it's always useful, and well, right now maybe it's not of importance, but let us assume that we always add everything. That's always complete. So, okay. I mean, what would I like to say before the break? So, right here, I mean, right above, this, looks maybe a bit strange, right? So we introduce some notion. For instance, why, if we already have a filtration, why don't we like just to upgrade it and to replace each ft by ft plus, right? Because if I just do such an upgrade, then of course this measurability condition, I mean, for the process, I mean, this notion of adaptedness, of course it survives, right? Because I just increased the sigma algebra. So of course it stays measurable with respect to fs plus, right? So if I go this way, then this is natural. But if I start with a random process, then this is something given, I mean, so I cannot choose it, right? And then it might happen that this is exactly, I mean, not ft. This is strictly large. Okay, I think let us make a break here and continue in 15 minutes. And it seems that I will need some time after the end of the second hour, sorry. So okay, let us continue. 3 misprints actually are corrected. I mean, okay, Mariana told me that the numeration actually is lost, so it should be 4, not 5. And more importantly, here I missed the indices. So, okay, trivially should be t less than s. So, okay, yet again, what's going on? Just the basic example you should have in mind is that we already have constructed some process, right? And then we denote these sigma algebras, I mean, we just introduce them by saying that these are all possible events that can be explained, I mean, can be defined in terms of the values of your process until time t. Okay? If you do this way, then it might be an issue because, okay, it might happen that this is strictly greater than ft, and we will see a very simple example. Okay, now an important definition. Maybe let me continue right here. Is a definition of stopping times. So, definition. The function tau defined on the probability space, I mean on the huge probability space, measurable function with values in either 0t or r plus, or in principle you can also admit infinite value. So you can enlarge your space of time with times with infinity. So it's called stopping time or optional time if you teach math finance, or Markov moment if you are more classical. If for any t, the event tau is less than t, right? I never remember, sorry for that. Okay, if the event tau is less or equal than t, is measurable.
And t is less than infinity,
Tau, well, as I mentioned, it's not necessary. So in principle,
stopping time.
I mean, so in principle, it's not necessary. So for instance, when we'll speak about strong Markov property, it works if you also allow that the stopping time is infinity with probability not 1. I mean, that it might happen that you indeed stopped when the process ran, but it also might happen that you just failed. Okay, in principle, this is allowed. Otherwise, I just said that this is a function to this space, right? And because of that, it's bounded. Okay, so if this is in Ft. And there is another definition. Weakly stopping time. If this event is in Ft. We are going to have an example just in a minute. I mean, what's the difference? So first, there is a trivial remark. This should be indeed a weaker notion, just because this event is the union over all rationals less than t. The event tau less or equal r, right? And because of that, if we know that each of these guys is in FR, then this is of course in FT. So it means that indeed the first notion at least implies the second. Okay? It's clear what happened. So, and the second remark is that so it means that just stopping implies the weakly stopping. And the second remark is that weakly stopping is equivalent to saying that this event is an FT plus. So the difference is that we just basically put plus here. Why? Again, it should be something very simple, just because this is an intersection over all strictly larger rationals of the event tau less than r. So if we have a weakly stopping time, then okay, this is measurable in FR, right? But it follows that the intersection of them, because they're nested, the intersection of them is in FT plus. Question? Nope. Okay, so that's why this implies that, and the other way around. Well, you just do the same as the line above. So basically, you say that if you already know this and you would like to analyze this event, then again you write it in this way. Maybe you have here FR plus, but it doesn't matter. The result is still in FT. Okay, so what is the difference? I mean, let us consider an illustrative example. That it might be something here. So, an example. Okay, I'm just going to define a process. And moreover, it's going to be a process with continuous trajectories, because we could have an impression that this is something about continuity, right? Why at all? I mean, if say xt is continuous, almost surely or just surely, why at all this ft plus should contain more information, right? Because, I mean, if there is anything right behind the point t, if xt is continuous, the answer is yes, it could be. So here is an example. Imagine that the process is defined in the following way. You just sample your favorite variable with discrete set of positive values. I don't know, 0, 1, just a fair coin. Or maybe slightly more involved, just pause. With some parameter, say 1. And then the process xt is defined in the following way. So this is 0 until the value of this xi. And this is, say, t minus xi after that. Okay? So what is the trajectory? It just waits until the output of this variable and then starts growing. So here is the trajectory of the process. Okay? So what is, say, f0? x0 is always 0, so we have no information at all. Imagine that f is now, okay, let f be generated by x, meaning that ft is generated by the values of the process up to time t. Okay, like in this model example. Then, what is f naught? There is not that much there, right? I mean, it's just a trivial sigma algebra. Well, if we've completed it, maybe there are also some other sets of zero probability, but if we do not complete it, then it's just trivial. Okay, what is f0 plus? What I claim is that it's bigger. Basically, it already knows if the output is 0 or not. Okay? It's clear on this example. I mean, because if I already, if I slightly enlarged my point, I mean, if I consider any integral, then I already know if I started growing or not. Okay? Etc. So basically, what you have is that Fn, okay, it was there, is strictly less than Fk plus, which is Ft and which is Fk plus 1 for any t on, okay, in between. So what is the message? What is the bottom line here? The bottom line here is that Ft plus contains more information in general than just Ft. Yeah. So in general, if you just say, okay, let me start with a process, and then let me define the filtration this way, then the notion of stopping time and weekly stopping time are different. Good. So another example of stopping times. Which is, in a sense, okay, well, this is the most useful and in a sense also general. Any stopping time can be written in this way. So those are heating times. So what's that? You fix some subset of R, and you just OR the target space. So if your process is not real valued, but say vector valued, or maybe even some more complicated stuff, so this is in target space. So by definition, this is just infimum of all t such that xt is in B. Again, in general, there are some issues, I mean, in between stopping time or weekly stopping time. So if xt has continuous trajectories, then, again, I never remember. So first, if B is open, then tau B is weekly stopping. Why? Just because the event that is strictly less than t can be written as the union over whatever n, for instance, of the event x t plus 1 over n is in B. So what's going on? If I have an open space, then the event that, nope. What would I like to say? This is the union over n, okay. Union over R is 0 t plus 1 over n xr. So what I'm going to say is that the event that our trajectory is here I mean, at some moment after a given t, I mean, it can be encoded by the values first only at rational points, right? Because the trajectory is continuous. And second, okay, if I just, slightly enlarge my my time interval, then I know that I'm already inside there. I mean, so if it was a trajectory and it entered, then, okay, it means that it was there in some neighborhood in time of this time. Okay, so this is indeed, and it should be here, it should be, yeah, it should be cap, right? Now I think I'm done. Yeah, not very good, right? Well, now at least it's correct. I mean, so again, if I know that my x tau is in B, xt is in B, right? So this is exactly the definition what it means that tau B is less than t. I know that, okay, xr is in B for some r which is at least tau B, but less than tau B plus 1 over m. What I'm saying? If anybody can correct me. So what is the event that tau B is less than t? It means that I've already reached the set B at the time t, right? For some r until 0 t. Okay? Well, this is an exercise. This is the last escape, just to say that, okay, I cannot fix all the quantities, but this is an easy exercise. So let us concentrate and go through. So, okay, what does it mean? It means that on 0t, right, it was a point on, okay, for some, yeah. So what is this, what's the important situation? Just imagine a continuous trajectory, I mean, just something very simple, which is going to enter an open disk, right? What is the stopping time? The stopping time is when it crosses the boundary, right? Exactly at this time, this is still not there. So this is why I should slightly enlarge it, okay? For some r here, and for any n. So that's what should be said.
But then you're going to describe the event that tau B is not greater than t, but not strict levels.
Then I'm going to describe the event that this is, yeah, this is, and this is in ft plus. This is in ft plus. Okay. Another example is, and it's going to be an exercise because that's even more complicated construction. If B is closed, then in fact this is stopping. Question? So I mean, I use this equivalence here. I use the equivalence B. So instead of describing the event that tau strictly less than t and proving that it fits into ft, I prove that this event fits into ft plus. Okay, so if B is closed, then tau B is stopping, and let me just write the construction. So this is, yeah?
B could be any set or from sigma?
In principle, yes, but I'm going to comment it in the next line. I mean, yeah. The answer is that for any Borel set, it works, but this is a deep result. And the problem is, as far as I understand, when it's not completely obvious why you can pass to the complement. So you can intersect and take unions, but what's not easy is to take a complement. So it's stopping, so let me just write the construction. So what's that? I should take union overall rationals, intersection again over all n, union over all rationals slightly before t of the event, the distance from xr to b is less than 1 over n. Okay, just an exercise. I already was not that good, I mean, with the first one. Just check that it works. I mean, the idea is that it should be rational points that are arbitrarily close to B before this time. Okay, then, you know, you should, work a bit. And then C, this is basically the answer to a question. So if B is Borel, it also works, but this is a deep fact. And we do not need it. Just,
Sorry, when you say it works, you mean it's weakly stopping?
Yeah, it's weakly stopping, exactly. Well, it couldn't be better because already with open sets, well, I think it's fairly easy to cook up an example, say with that. It's weakly stopping indeed. Okay, good. So we have some stopping times, and then I think what we do next is to prove weak Markov property of the Brownian motion. So let it be, say, 4.2. The Brownian motion and 0, 1 low. Just yeah, we're ready to so here is the proposition. And somehow again remember this discussion that ft plus is not ft. So let bt be a standard Brownian motion. And Ft be the sigma algebra generated by dt. Then imagine we have some deterministic time, some s. Then for any fixed s, and this is exactly why it's called weak. The process b t plus s minus bs, like that, the increments, is again a standard Brownian motion, which is not a big deal. Which is independent of fs plus. So the conceptual claim is that the increments after the time s, they do not know anything, I mean, in this gap, not anything about this gap. Okay? Well, the proof actually is fairly simple. So basically, what should we do to prove this independence? Let us consider some event in fs plus and some bounded continuous function f of p variables. So we need, what we want, is to prove that the expectation of the indicator of this event by let me denote it somehow. Okay, maybe in the next line. So t1 plus s minus bs, etc. t p plus s minus bs. That this converges to the expectation, to the probability of A by the expectation of, it's not converged, this is equal, by the expectation of this function computed at bt1, bt. So this is what we need. Why? Because first imagine that we take A to be the full space, right? Then we just forget about this indicator, this probability is 1, and what we see is that all the finite dimensional distributions, I mean, you can vary this f, so, and varying this f, you see that all the finite dimensional distributions, all the increments, actually converges to this, right? So, I mean, if you take A first to be omega, you see that this is indeed the Brownian motion, and then this is exactly the independence condition. It's clear, I mean, that this is exactly the condition we need to check. Okay, good, so if A is omega, then Brownian motion, and then general A dependence. The only thing which might bother us a bit is that, okay, why these are independent, right? So this is exactly the claim that we can put here plus. But this is a very small, very teeny issue just because, okay, take now instead of S, some approximations from above. Take Sn to be whatever, S plus 1 over n. Okay? And then note that here we have an independence. Tn plus Sn, etc. Now, minus b Sn, etc. Now, okay, what's the picture? The picture is that A lives here. Maybe, okay, it's an intersection of everything which is further. All the increments, so here is Sn, all the increments lives there. Okay, those are independent. So this is the probability A by the expectation on f bt1, etc. Right, because we know that this is basically the Gaussian distribution, the same with this distribution, and independent of f s plus. Okay, and now just take the limit. So we know that the paths of the Brownian motion are continuous. So because of that, we know that these increments do converge to the increments with s instead of Sn, almost surely. Okay? And then you just say that by the dominated convergence theorem, so everything here is bounded, and f is a continuous function. So this converges to the same with s. So what's used? We use that f is continuous plus dominated convergence. Okay, good, not a big deal, right? So that's something clear, but still it has some consequences. So again, so there is absolutely nothing surprising that this is distributed as the Brownian motion, right? This is still a centered Gaussian process with the same covariance. I mean, of course, not an issue. The only issue is here with the plus, but again, there is nothing very deep. You just push yourself a bit further and then, go back by continuity. Okay, but still it has corollaries. Which are 0, 1 lows. Okay, what's that? If some event is an f naught plus, in the conditions, of this proposition, so ft is the filtration generated by the Brownian motion, then it must have a trivial probability, either 0 or 1. Well, there is nothing to prove here because, okay, any event, any such an event, this is on the one hand in f naught plus, but on the other, this is, say, whatever, in f1, This is in the big sigma algebra generated by the Brownian motion. And we know that the Brownian motion is independent. The whole Brownian motion is independent of f0 plus. This is exactly the content of this theorem. Okay, so these two guys are independent. And because of that, the probability of, say, A intersected with A is probability A, right? So, okay, this is the standard a bit esoteric reasoning, right? So if the event is independent of itself, it must be either of 0 or 1 probability. And each event here is such. Okay, good. Then, of course, there is a question if there are any reasonable events. So we are just doing some abstract nonsense, proving some lemmas. But if we can use it in some way, the answer is yes, we can. In particular, still, yes, we can. In particular, okay, in the following way. So let us think what happens with the Brownian motion exactly near the origin. We know that it is not Lipschitz there, for instance. We know that it has some models of continuity, though it's still not proven. Let us think about some very rough properties. So what I'm going to prove is that the probability of the event, this is just an illustration to the 0-1 law, that the probability of the event that for any S, the maximum over 0S of BT is strictly positive is 1. What does it mean? It means that it cannot happen that the Brownian motion becomes negative immediately. That on any interval there is a positive, there is a point where it is positive. Okay, how to prove? First, just note that this is in, that this event is in F0 plus, right? Just by the very definition. Second, so it must be either of probability 1 or of probability 0. Okay, the probability 0, well, is slightly suspicious. How could it be? But the formal reasoning is, for instance, the following. So we know that BT is not Lipschitz. It's 0. And because of that, we know that the probability of the event that BT K is greater than Tk along the subsequence, along some subsequence into 0 is 1, right? So we know that it cannot happen that Bt is less than T. Because of that, we know that the probability of the event that it is actually positive and greater than Tk, it could be without absolute value here, along some subsequence, is at least 1/2. Right, so in principle it could happen that the Brownian motion is such a nasty object that it becomes immediately negative. Very strange, but always negative, very strange. But we know that by the symmetry, well, either it happens along a positive, either it's positive, or either it's negative, and by the symmetry, each of the probabilities is at least 1/2. Okay, we are done because okay, we know that the probability is non-trivial, and this is in the trivial sigma algebra. Okay, this is just an illustration of how this can be used. I mean, this is an illustration of the event, which is not tautologic, right? And which lies here, which belongs to F0 plus. Okay, just a remark. Since we know that this is invariant under inversion, we can translate the 0,1 law to the infinity instead of the 0. So for any A which is in the so-called tail sigma algebra, so which is the intersection over all okay, which is what should I write here? So, which is measurable with respect to the tail of the process. I mean, to the event that can be formulated in terms of time starting from some point. I mean, okay, so this is, yeah, well, this is sigma algebra is generated by the process Bt with t greater than t. The intersection over, say, this t. That any event here is also has a probability either 0 or 1. Right? Because this is just the same sigma algebra. Okay, good. So, yeah, as I suspected, so I need more time. So we have another break and then continue without exercises. So sorry for this. Yeah, what's the next? We should prove today the strong Markov property. And the strong Markov property is exactly the same result. I mean, like here, but not for the fixed time, rather than for any stopping time. So this is a deeper result. And okay, we're pretty close, but still, I need another an hour.